Hello everyone, my name is Dr. K.C.H. Apparao, working as an associate professor in mechanical engineering department. In previous class, we discussed the LMTD method, derivation of heat transfer rate by using the LMTD method for the parallel flow heat exchanger. So in this class, derivation of heat transfer coefficient derivation of heat transfer coefficient Q for the counterflow heat exchanger by LMTD method. Okay. So this is the question which is given in the question bank. Derive an expression for LMTD in case of counter current flow double pipe heat exchanger. Okay. We will address this derivation. This is the temperature profile. So you know this one. We know this. What is counterflow? Counterflow heat exchangers mean heat transfer takes place between the two fluids which are separated by some wall. Hot fluid enters, THA, hot fluid outlet, okay. So cool fluid enters here, just opposite to hot fluid outlet. So cool fluid leaves here, outlet, okay. So here cool fluid direction is opposite to the hot fluid direction. It means in counterflow heat exchanger, both the fluids flow parallel to each other but in opposite direction, in opposite countering direction, opposite direction. Then the temperature profile is like this one. Hot fluid enters here, cold fluid outlet here, hot fluid outlet here, cold fluid inlet here. Okay, so this is the delta T1, this is the delta T2. Just compared to parallel fluid exchanger, this is little bit difference. In parallel fluid exchanger, both inlet temperature we will see one side, both outlet temperature we will see another side. So here just crossing outlet hot fluid inlet to cold fluid outlet to one side. So that is nothing but this difference is equal to delta T1, hot fluid outlet to cold fluid inlet to another side. So this is delta T2. So this is the difference, main difference between the counterflow heat exchanger. We will see same assumptions also here. You can refer this one. Flow is parallel but in opposite to each other. So hot fluid inlet to hot fluid outlet to, but cold fluid inlet here, cold fluid outlet here. This is delta T1, this is delta T2. Okay, so we will see same assumptions what are taken in the parallel heat exchanger. Here also we consider those assumptions. U, overall heat transfer coefficient, is constant throughout the heat exchanger. Potential and kinetic energy is also negligible. We are not considering energy differences. Specific heats CH and CC, we are assuming these are the constants. Heat exchange takes place only between the two fluids. We are taking only heat exchange between two fluids. That is the assumption. Temperatures of both the fluids, hot inlet to hot outlet, cold inlet to cold outlet. So these are the constant over the entire cross section. Okay, next you know that to derive this derivation for the entire heat exchanger, initially we will take small elemental area, then we will derive the, for the small elemental area. So we will derive the rate of heat transfer for the small elemental area. Then we will integrate this one with respect to with the help of the limits. Then we will get the overall rate of heat transfer for the entire heat exchanger. Okay, so basically we will see small elemental area. Okay. It means this is the hot fluid inlet, hot fluid outlet, cold fluid inlet, cold fluid outlet. Okay. So this one is the delta T1, T2, This one is the delta T1. Sorry. Okay. We are taking the small elemental area for this one. This is the dx data, T thickness. So distance x from 1 to 2. So here this is the dth, this is the dtc. This one is nothing but delta T. Okay. So similar to here, temperature profile is in both conditions decreasing order. Here also here. So we are taking the enthalpy energy balance for the small elemental area. So in both conditions we take minus because the graph is decreasing order. So here heat transfer rate of heat transfer for the small elemental area is equal to minus mhch into dth. So mhch is nothing but capital CH. Okay. So dq is equal to minus mccc into dtc. Okay. So mccc will write to capital Cc, specific heat of the cold fluid. So in both conditions minus because it is decreasing order. Okay. So next to temperature difference for the small elemental area, that is the delta T. We will take delta T is equal to Th minus Tc. We will derive this derivative in both directions, both sides. Derivative of delta T is equal to dTh minus dTc. You know this one. Okay. Okay, dTh is equal to here. dTh you can rewrite like this one from this equation is nothing but dq by minus ch. Similarly, dtc is equal to dq by minus cc. Okay. So these values we can substitute these values here, dTh and dTc. Then the formula will be like this one. For the dTh is equal to dq by minus ch. So minus dq by ch. Minus of minus into dq by cc. So minus of minus plus. Then the formula will be like this one. You can take. Okay. What is that one? Derivative of delta T is equal to dq. Because here dq is the common term. You can take common dq. Then minus 1 by ch plus 1 by cc, or 1 by, if you take minus is common, then 1 by ch minus 1 by cc. 1 by ch minus 1 by cc. You know this one. Okay. So here delta temperature profiles, you can send this delta T also to left side. Then the formula will be like this one. Okay. Derivative of delta T by dt is equal to u into 1 by ch minus 1 by cc into dA. So dA is the small elemental area. Okay. Elemental area. Then we got that equation. If you integrate this one in both direction with respect to limits, then we will get the rate of heat transfer for the entire heat exchanger. So counterflow heat exchanger. Then derivative of this one with respect to limits is equal to delta T2 to delta T1. You know this delta T1 values and delta T2 values in counterflow. Here limits is equal to session 1 to 2. Okay. Like this one. Delta T2, delta T1 is the limits, because once again so THA, this is the TH naught, TCA, TC naught. So this is the delta T1, this one is the delta T2. Delta T1 is equal to THI minus TC naught. Delta T2 is equal to TH naught minus TC. So this is the value, so you can remember this one. Then if you integrate this in both directions, okay, delta T by dt, if you integrate this one, then we will get to delta T. If you apply the limits, delta T2 minus delta T1, so log A minus B is equal to log A by B. You can write like this one. So ln delta T2 by log A minus log B is equal to log A by B. Okay. Ln delta T2 by delta T1. You can rewrite like this one. Otherwise, so integral of that one is equal to delta T. If you apply this limits, so that is the delta T2 ln delta T2. So this one is equal to ln delta T, ln delta T2 minus delta T1. Okay. So if you rewrite like this one, you will get this formula. So ln of delta T2 by delta T1 is equal to minus integral of dA. So area is uniform for the entire this construction. So then integral of dA is nothing but A. Okay. Then minus UA into 1 by CH minus 1 by CC. Okay. So you know this one. Then we know the energy balance equations for the hot fluid and cold fluid with respect to thermodynamics formulas. Okay. So those are the Q is equal to same mHCH into hot fluid temperature difference. So mHCH is nothing but capital CH. So specific heat of the hot fluid into hot fluid temperature differences. Okay. So we required, according to this formula, we require the 1 by CH and 1 by CC. Then you can rewrite like this one. So from this one, we can rewrite like this one. 1 by CH is equal to hot fluid inlet minus hot fluid outlet by Q. Similarly, for the cold fluid, MCCC into TC0 minus TCA. So MCCC is nothing but a capital CC, specific heat of the cold fluid, into TC0 minus TCA. Then 1 by CC is equal to TC0 minus TCA by Q. Okay. So we can substitute these values in the previous formula. What is the previous formula? Here. So in this case, we can substitute those values. Okay. Then the formula will be like this one. ln delta T2 by delta T1 is equal to minus UA into 1 by CH minus 1 by CC. Okay. So this is the formula. Here we are substituting the values here and here. Okay. 1 by CH is nothing but THA minus TH0 by Q, like Q. Here minus 1 by CC is nothing but TC0 minus TCA. So this is the Q. So Q is the common term. You can take common here. Okay. So the formulas will be like this. Then you can convert these temperatures into delta T1 and delta T2, because you know that delta T1 is equal to hot fluid temperature of hot fluid inlet minus cold fluid outlet. Delta T2 is equal to hot fluid outlet minus cold fluid inlet. Okay. So we can rearrange these temperatures like this one. Okay. So THA minus, we require TC0. Here TC0 you can write first here TC0. Okay. Then you can take minus of, then TH0 minus, okay, minus and minus plus, for this one, for this minus taking common. So then this value is equal to TCA. Okay. You can rearrange this temperature. Then you know that this is the delta T1. This one is the delta T2. Okay. Then the formula will be like this. We are just here rearranged this one. THA minus TC0 minus of TH0 minus of TCA. So this is delta T1. This is delta T2. The formula is like this one. Okay. So ln delta T2 by delta T1 is equal to minus UA by Q into delta T1 minus delta T2. Then here minus is there. Just we can remove this minus by changing like this one. ln delta T2 by delta T1 is equal to UA by Q into delta T2 minus delta T1. Right? So we required Q, rate of heat transfer for the counter fluid exchanger. Then the Q formula is equal to UA into delta T2 minus delta T1 by ln of delta T2 by delta T1. Okay. Otherwise, you can rearrange like this one. You can rewrite like this one. First, I am taking delta T1 minus delta T2 by ln of here also delta T1 by delta T2. Okay. So this is nothing but delta T2 by delta T1. This is nothing but we can write like this one, UA into delta T ln. Delta T lm, delta T logarithmic mean, because you know this one, the reason behind this one is the temperature differences between the hot and cold fluid varies from point to point. So we are considering the logarithmic principles. So the finally rate of heat transfer for the counter fluid exchanger UA into delta T lm. So same formula for the parallel fluid exchanger also, but delta T1 values and delta T2 values are different in both conditions. Okay, in parallel flow, hot fluid temperature, inlet temperatures THA minus TCA, that is delta T1, but here THA minus TC naught is the delta T1. So these delta T1 and delta T2 values will be changed for comparing the parallel flow and counter fluid exchanger, but remaining same formula is same. Okay, so by using this formula we can find out the rate of heat transfer in counter flow heat exchangers. Okay, so we'll see. So this one is the one numerical. You can solve this one. Here water at the rate of 68 kg per minute, so mass has been given. Next heat, so water inlet temperature THA, TCA and TC not also given, and oil another fluid, so that is the hot fluid, that one specific heat has been given directly, C capital CH, and fluids are used to counter fluid exchanger. The oil enters the, so oil temperature THA also given, TH not also given. So four temperature, hot fluid inlet outlet, hot cold fluid inlet outlet has been given. So mass mass of the water, that one given. You know the specific heat of the water, that is the 4180. By using mass and specific heat, we can find out the so capital CH, CC cold fluid specific heat. Okay, MC into CC. Okay, so then you can find out the Q value. So QA is equal to MCCC into cold fluid temperature differences. So that is the Q value. So what you have to find out to, so you have to find out the area. Okay. If you know the Q value, then you know that Q is equal to UA into delta T lm. Then you have to find out the delta T lm. Delta T lm formula, you know this one, delta T1 minus delta T2 by ln of delta T1 by delta T2. Okay, so you know that delta T1 is this is the counter flow, so THA minus TC naught. Similarly, delta T2 is equal to TH naught minus TCA. Okay, so THA, so that is the 110 minus, so TC naught, so 75 degrees Celsius. So this is the delta T1. Delta T2 is equal to TH naught 75 minus 35. Okay, so these are the values. So by using this temperature, we can find out the delta TLM. Then if you substitute the values, you know that Q value, you know that the overall heat transfer coefficient also given, that is the 320. And you know that delta TLM already we just solved that one. Then you can find out the area. By using this formula, you can find out the area. Okay, in this way just we can solve this numerical. So thank you listening this class. So this is the final answer. You can refer this one. Okay, these are the different textbooks you can refer to solve more number of numericals based on the counter fluid exchanger. Thank you listening this class.
Like, share and subscribe. Hit the bell icon for more updates.
1, 2, 3, start. Good morning, my dear students. My name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. Okay, listen, from few classes we are discussing the question bank questions, critical thinking questions, and different numericals also. So in this class I would like to explain about the NTU method for designing of heat exchanger of mainly parallel heat exchanger. So how to derive the NTU, so or derive an expression for NTU in case of parallel flow double five heat exchanger. This is given in the our question bank. We'll derive this one. Okay, so few more questions which are related to this one. Discuss the advantages of NTU method over the LMTD method also. Why how to choose the NTU method? Because already you know that LMTD method. So why how to prefer the NTU instead of LMTD? So this question also will address this one. Or expression the effectiveness of NTU method. So that is the formula, you know the formula. So that is the 1 by exponential of minus NTU into 1 plus C by 1 plus C. So this is the formulas we will derive here. Okay. So the first NTU is the alternate method of heat exchanger. So this is nothing but effective NTU method. You know this one. So NTU is nothing but number of transfer units. Okay. So this is the NTU. Okay. Why how to choose the NTU method? Because origin of this method is based on the fact that you know that for LMTD method, design of heat exchanger by LMTD method, we should know the 4 temperatures. It means hot fluid inlet we should know, and the hot fluid outlet also we should know. Cold fluid inlet we should know. Cold fluid outlet also we should know. Okay. So some cases it means in practice outlet temperature of the fluid stream from a heat exchanger may not be available due to heat exchange is being connected to a downstream processing unit. So in this case we can't measure the outlet temperatures. So in this case we have only inlet temperature, hot fluid inlet and cold fluid inlet. So remaining hot fluid outlet and cold fluid outlet we should not get those values. So in case of only inlet temperatures are available, then we can't design the heat exchanger. We can solve the rate of heat transfer by LMTD method. So in that case we have to prefer the NTU method. So by using the NTU method we can solve the rate of heat transfer Q by using only inlet temperatures. Okay. So we'll see in case of some only outlet temperatures are available. So inlet temperatures are available, not outlet temperatures. In case we prefer the NTU method. So for these cases LMTD is not suitable. Already explained this one. So effectiveness is nothing but NTU method. Effectiveness is equal to actual heat transfer by maximum possible heat transfer. You know the formulas for actual heat transfer, that is represented by Q. But we see what is maximum possible heat transfer. Maximum possible heat transfer Q max. What is Q max? We'll see here. Okay. These are the formulas for the actual heat transfer coefficient. Q is equal to, for a hot fluid, you know this one. Q is equal to, this is the cold fluid, you know this one. Okay. So how to find out the maximum heat transfer coefficient? Q max value could be attained if the fluids were to undergo a temperature change equal to maximum temperature difference. It means Q max occurs when the temperature difference delta T is maximum. Maximum means hot fluid inlet is the highest temperature and cold fluid inlet is the least temperature point. So the difference between the hot fluid inlet and cold fluid inlet, that shows the maximum temperature difference. If you consider this one, that is nothing but Qmax. So if it is difference is maximum, automatically specific heat, that is should be minimum. So C minimum into inlet temperature differences, that is the value, that is nothing but mm, Qmax. Okay, Qmax is equal to, that is the formula. So here you can see hot fluid inlet is equal to cold fluid outlet. Here cold fluid range is very high. So T C naught minus TCA, in this place T C naught is nothing but THA minus TCA. Okay, so temperature difference is very high. So in this case CC should be minimum. So CC should be minimum, then temperature THA minus TCA. Okay, so CH is greater than CC here. If you hot fluid outlet is equal to cold fluid inlet, it means so hot fluid temperature difference is very high here. So CH is very minimum. So CH, in place of CH you can write C minimum, then temperature difference THA minus TCA. Okay, so how to take TCH and C minimum and C maximum. Okay, here just like I'm taking CC is the C minimum compared to CH. So I'm taking CC is the C minimum, automatically CH is the C maximum. Then the formula effectiveness is equal to Q by Q max. Okay, so Q with respect to CC I'm taking. So that is nothing but capital CC into TC naught minus TCA. Okay, so Q max with respect to CC means that is the C minimum into hot fluid inlet minus cold fluid inlet. Okay, here C minimum, that is the CC. So this is CC. This CC will be cancelled. Then effectiveness is equal to cold fluid outlet minus cold fluid inlet by hot fluid inlet minus cold fluid inlet. So this is the formula. You have to remember this one. This is the equation 1. Okay. So we know that these are the energy formulas according to thermodynamic principles. So Q is equal to MHCH is nothing but capital CH. So hot fluid inlet minus hot fluid outlet. So temperature differences of hot fluid. So here MCCC, TC naught minus TCA. So CC is the specific heat of the cold fluid. Okay, so we know that from this equation we can rewrite like this one here, because CC I'm taking C minimum. Okay, so C minimum by C maximum, nothing but capital CC by capital CH. The formula will be like this one, MCCC or MHCH. This is CC, this is CH is equal to hot fluid temperature difference, cold fluid temperature differences. Okay, just remember this equation also. Next, you know that this is already derived in the LMTD method. Just you are taking that this formula directly from this method. You know that ln delta T2 by delta T1 is equal to minus UA into 1 by CH plus 1 by CC. Okay. Okay. So here, you know that here delta T2 and delta T1 values also we can substitute according to parallel fluid exchanger. So that is delta T2 is equal to hot fluid temperature outlet minus cold fluid outlet by delta T1 is the hot fluid inlet minus cold fluid inlet is equal to minus UA into C minimum. C minimum means here 1 by CC plus 1 by CH. So CC is the C minimum, CH is the C maximum. Just we are taking C minimum here. Minus UA into C minimum means 1 plus C minimum by C maximum. So that is the formula. So then in ln of this is the temperatures, you know this one. We are taking UA by C minimum. UA by C minimum is NTU. So number of transfer units. So we are taking number of transfer units, or we can represent this one also N. N is equal to UA by C minimum. In place of UA by C minimum, just I am writing NTU. plus 1 by C minimum by C maximum. Then you know that formula. So just this is the ln, we are sending this ln to right side, then it will be exponential. Then temperatures, hot fluid and cold fluid outlet minus hot fluid and cold fluid inlet is equal to exponential of minus NTU into 1 plus C minimum by C maximum. You know this one. Okay. So here we know another formula. So just here I am adding for the simplification of this one, TH naught minus, I am adding minus TCA plus TCA. Okay. We already know that formula. What is C minimum by C maximum is equal to THI minus TH naught. Equation 2 already know that THI minus TCA. So by using this formula, we are deriving TH naught. So TH naught is equal to like this one. We can see TH naught. So TH naught is equal to, just I am giving TH naught. So TH naught is equal to THI minus C minimum by C maximum to TC naught minus TCA. Okay. So substitute this value here for the simplification. Then equation is like this one. Okay. If you simplify this one, so here, then you will get this equation. Okay. THI minus TCA by THI minus TCA. So both are same. So it will be cancelled. So TC naught minus TCA by THI minus TCA. So this is the Q max. So effectiveness, you know that effectiveness is equal to Q by Q max. Okay. So this is the Q. This is the Q max. Okay. So here we can write the effectiveness. Here also we can write the effectiveness. The formula will be like this one. 1 by C minimum by C maximum into effectiveness minus effectiveness. So this is equal to exponential of minus N2 into 1 plus C minimum by C maximum. Okay. So then the formula will be like this one. Okay. We are sending the minus also another side. So then effectiveness of 1 plus C minimum by C maximum is equal to 1 minus exponential of 1 plus C minimum by C maximum. Just we are sending this one. We have to find out the effectiveness. So effectiveness is equal to, this is the formula. Okay. 1 minus exponential of minus NT into 1 plus C minimum by C maximum. Okay. So this is the formula. You can rewrite like this one for simplification, for remembrance. So 1 minus exponential of NP is nothing but we can represent this is an C minimum by C maximum. We can represent this is a C. Okay. 1 minus exponential of minus N into 1 plus C by 1 plus C. Okay. Because you know that N is the NTU. NTU is nothing but UA by C minimum. C is nothing but C minimum by C maximum. So this is the effectiveness formula. Okay. You can solve the numericals which are related to counterflow by using the effectiveness in case only inlet temperatures are given. Okay. So this is the one numerical. So you can see this one. Okay. So in next class we will see only numericals which are based upon counterflow and parallel flow. So just I am leaving this one. So these are the different textbooks we can refer to understand the concept of NTU method, especially for the parallel fluid exchanger. Next class we will see the NTU method for the counter fluid exchanger. So thank you listening this class. Thank you.